Hey guys, just to recap everything we discussed in class today as far as end behavior of polynomial functions. The end behavior of a function's graph is the behavior of the graph as x approaches positive infinity or negative infinity. And this is the notation we use, plus infinity or minus infinity. For the graph of a polynomial function, the end behavior is determined by the function's degree and the sign of its leading coefficient. So those are the only two pieces of information we need to know to determine the end behavior. Now the two types of degrees that we discovered today were odd degree, or even degree, and even degree. The two types of leading coefficients we worked with today were positive, and negative, and negative. So those are your only two options for either of these two pieces of the polynomial function. The degree is either going to be odd or even, and the leading coefficient's either going to be positive or negative. Once you know what those two pieces are, you can determine exactly what the function does as x approaches negative and positive infinity. So for here, if we have an odd degree with a positive leading coefficient, as x approaches negative infinity, our function is going to decrease and approach negative infinity. As x approaches positive infinity, our function is going to increase and approach positive infinity. For an odd degree and a negative leading coefficient, as x approaches negative infinity to the left, our function is increasing and approaching positive infinity. As x is getting bigger to the right, our function is decreasing and approaching negative infinity. If we have an even degree down here, and our leading coefficient is positive, as x is getting smaller, what's the end behavior? On the left here, our function is increasing or approaching positive infinity. And as x gets bigger, to the right, our function is also increasing and approaching positive infinity. If we have an even degree and a negative leading coefficient, our function is just going to flip. So as x is getting smaller here, our function is decreasing and approaching negative infinity. And as x is getting bigger, our function is decreasing as well and approaching negative infinity. So here's our cheat sheet for polynomial functions. Once we have our two pieces of information, our leading coefficient, whether it's positive or negative, and our degree, whether it's odd or even, all we need to do is match those up and work with either 1, 2, 3, or 4 boxes. So once you know, you're just going to crisscross. So for positive, odd, we're going to go positive, odd, and work with what's in this box. Positive, even is going to be in this box. Negative, odd will be here, and negative, even will be here. And this works for all polynomial functions as long as the degree and the leading coefficient match up, regardless of what those numbers are. So for odd degree and positive leading coefficient, as x approaches negative infinity, our function is going to approach negative infinity. As x approaches positive infinity, our function is going to approach positive infinity. Sticking with odd degree for negative, all we're going to do is flip-flop our function over the x-axis, right? So as x approaches negative infinity, our function is going to approach positive infinity. As x approaches positive infinity, our function is going to approach negative infinity. So for the evens, as x approaches negative infinity, if we have a positive leading coefficient, our function is going to approach positive infinity. As x approaches positive infinity, our function is also going to approach positive infinity. Remember, if we have an even degree, positive just means that our function is opening up because it looks like a parabola. If we have a negative leading coefficient, as x approaches negative infinity, again, our function is just going to reflect over the x-axis. So this is going to be negative infinity. And as x approaches positive infinity, again, our function is going to approach negative infinity. So all of your answers will look like something in one of these 4 boxes, depending on what your degree is, odd or even, and what your leading coefficient is, positive or negative. All right, let's run through a couple quick examples here. So if we take a look at number 25, we have a function where as x approaches negative infinity, our function is approaching positive infinity. And as x approaches positive infinity, our function is also approaching positive infinity. So what do we know about this function's degree? It has got to be even. what do we know about its leading coefficient? If our function is opening up in both directions, our leading coefficient has to be positive. And all of this should match up with what you guys wrote down on your little cheat sheet. So for number 26 here, as x approaches negative infinity, our function approaches positive infinity. And as x approaches positive infinity, our function is decreasing and approaching negative infinity. So the end behavior here is opposite, so this degree has to be odd. Once we know that it's odd, what is the leading coefficient? If we're starting from positive infinity and as we increase we're going to negative infinity, that means that the leading coefficient of this odd polynomial function has got to be negative. Okay, and the last one here, as x is approaching negative infinity, our function is decreasing and also approaching negative infinity. And as x is getting bigger and approaching positive infinity, our function down here is also decreasing and approaching negative infinity. So we're decreasing on both sides, which means our degree has to be even. And because this even polynomial function is opening down, our leading coefficient has to be negative. So this is where you guys need to start taking notes. This is the new material which was not covered in class. So take a couple minutes and copy down everything you see on the screen. Press pause. So in class today we discussed the end behavior of polynomial functions. And we disregarded what was going on in the middle of the function. So turning points here refer to what happens in the middle of the function. Depending on what the degree is, you're going to have some turning points. Those turning points are determined by the degree. So if you look down at the key concept box here, number 1 says the graph of every polynomial function of degree n has at most n minus 1 turning points. So whatever our degree is, we can have at most one less turning points than what the degree of our polynomial is. So don't worry so much about number 2 because we're not going to worry about what the distinct real zeros are as far as graphing goes. But you guys need to know how many possible turning points a polynomial function can have in regards to what its degree is. So if we take a look at this polynomial function up here, we have no idea what the function is, but just by taking a look at it, we can kind of guess what kind of function it is, right? As x approaches negative infinity, what does our function approach? Negative infinity. As x approaches positive infinity, our function approaches positive infinity. So we're going in opposite directions, so this looks like it's going to be an odd degree polynomial function. Now because we have one local maximum and one local minimum, we have 2 turning points. Now, I like to kind of refer to these things as peaks and valleys. So if you're going along the graph here, you're going to hit a peak at this point, the local maximum. Then we decrease a little bit and hit a valley, the local minimum. Then we start increasing again. Okay, so if we have 2 turning points, what's the degree of our polynomial function? If the turning points is 1 less than our degree, this looks like it's going to be a cubic function. What's the leading coefficient going to be of this cubic function? If as we go to the left here, if x gets smaller, our function is decreasing. As x gets bigger, our function is increasing. So we know our leading coefficient has to be positive. So this function is going to look something like f of x equals x cubed, and there might be something else going on here. Those are ellipses, just a couple dots, because there might be something after the x cubed. But we know because our degree is 3, we can have at most 1, 2 turning points in our function. So these turning points are called local maximum and local minimum. You may also see the word relative maximum and relative minimum. So let's just write this down here. So relative is the exact same thing as saying local. So relative max, local max, those are the same thing. Relative minimum, local minimum, those are the same thing. These peaks and valleys are also sometimes referred to as extrema. So extrema are just maximums and minimums. So if you're asked to find the relative extrema or local extrema of a polynomial function, what you're really looking for is just the local maximum and the local minimum of a function. So extrema just refers to both of these guys. All right, let's put this to practice. So on the left side here, we have a screenshot from a TI-83 Color Plus of a function x to the fourth minus 7x cubed plus 5x squared plus x plus 2. And on the right here, we have the graph of what that function looks like. So we can look at either the polynomial function itself or the graph and determine what degree it is. We have an x to the fourth, so our degree here is 4. Our maximum number of turning points here is 1 less than our degree, so n minus 1 gives us 3 maximum turning points. When we look back at the graph, we can ask this question: how many extrema does the graph have? It can have a maximum of 3 turning points, but how many do we actually see on the graph? It looks like we start at positive infinity and the function decreases, hits a valley, then increases, hits a peak, decreases again to hit another valley, and then increases again to positive infinity. So it looks like we have 1, 2, 3 extrema. So we have the maximum number of turning points for this function. So we have 3 extrema. How many of those are local or relative maximums? So it looks like we have one peak here in the middle of our function, and it looks like the coordinate of that peak is somewhere around 1, 3. And that's just a rough guess just by looking at this graph. How many local or relative minimums do we have? If one of these is a maximum, that means the other two have to be minimums. So we have a valley at this point here and this point here. And again, just a rough guess of what those points are. It looks like the first one is at 0, 2, and the second one is at 2, 0. So this point here also looks like it's an x-intercept for our function. The last question you guys are going to face will be whether or not we have any absolute maximums or minimums. So that just means if we're looking at this function, is there a extreme low value that this function hits? And it looks like we have the lowest point that this function will hit will be y equals 0. And this is referring to our y value. So the lowest this function will go on the y-axis will be y equals 0. If our leading coefficient, x to the fourth here, was negative, what would happen to our function? Our entire function would be reflected over the x-axis, and we would have an absolute maximum instead of an absolute minimum. So here's a problem you guys can try on your own. Here's your function on the left over here. This should be an x where this black square is. It got blacked out when I took the picture. So this is the function x cubed minus 2x squared minus x minus 4. This is a picture of your function on the right. I'd like you to answer what the degree is, what's the maximum number of turning points we have, how many extrema the graph has, what are the local maximum and minimum, plural if there's more than one, and what's the absolute max and min for this function. Good luck.